March 1st, I was going to put the exam for the last day of the classes. That plan is canceled. I canceled that one because we are losing one class. And no, it was not just that one. I'll tell you what. I thought about another thing also. With the homework is going to be a difficult thing. You are going to do your homework is going to be homework number 3 is going to be due when next week, right? Next Thursday. So which is the 25th. Homework number 4 is going to be due March 3rd, and homework number 5 is going to be due March 10th. That was the problem. I thought if I'm going to push it that way, again, homework number 5 is going to be a problem. When you're going to turn it in and the solution and those kind of things. I don't forget. We'll go with the regular schedule. What time is the exam now? 7 to 10 p.m. Friday?
Thursday.
Do you guys? We'll check. See if you guys want. Agree. We can break. I'll reserve the class. Maybe 5 or 6. I don't know how many we have. 3, 9. If you have 38, you have 55 in this class. If you don't have an exam that day, maybe we can start 5 o'clock if you want. Instead of going 7 to 10, we go 5 to 8. Something 5 to 8. We'll leave it for later to see. If you guys agree, we can start there 5 or 6. Up to you guys. 7 to 10, I think is pretty late for Friday, but up to you guys.
It's Thursday.
It's Thursday?
Yeah.
It's Thursday. It's not Friday. I hate Friday to be here 10 p.m.
This is actually towards more next quarter. Since your class would be 5 to 6:30 as usual, PC 180 is going to be 6:30 to 8. Are we going to have discussion after class still?
Yeah. What is scheduled now? 6:30 to 8?
Yeah.
Normal here, that kind of class here?
So his class is right after your class.
And then they schedule
Night shift,
So you're gonna have discussion after lecture still?
I want to have discussion after one of my classes.
Yeah.
His class is immediately following both of your classes. This is Monday, Thursday, 6:30 to
Oh, no. I told them to put my discussion session right after that. I told them already, Maybe you can bring 30 minutes ahead, something, we want to, I'm not sure, but it's not going to work out, because the class schedule is like that, so. Okay. Well, one more thing though, I was going to tell you. March 1st, we don't have a class, and there was one more thing for last.
So homework is not Tuesday or
Yeah, you can bring it Thursday, I'm fine. Did I say Tuesday or Thursday before?
Thursday.
No, Thursday. No, because now we have 2 more Thursdays to go, I can set the homework number 4 and number 5, for Thursday after, Yes, I think we have how many questions we have? I think 10 questions.
10
right?
questions.
So maybe, we can do that. So, then this part is going to be chapter 6. If you look at your book, it didn't explain what I'm going to say here, but I'm going to start with it, how to get to the equivalent circuit of the synchronous machine. I hate to put it on the board and say, oh, this is the equivalent circuit, I want to show you why we are using that circuit. You have to go through a lot of calculation. It's not in your book. But if you go check, there is another book, it's called Electric Machinery by Fitzgerald. I'm going to put it on the board, most of it. You don't have to go for the book. And that part, you're not going to have any question about it. But I want you to see the steps, how to get to the equivalent circuit of the cylindrical machine. I told you, synchronous machine, we have a cylindrical and we have a solid pole. Solid pole, I like to cover it, and I think we have time to cover it. I'm not sure how much you guys are going to follow, to be honest. That's another part. But I want to cover completely the cylindrical one, they call it cylindrical synchronous machine. We'll go over the basic of that, how it does work. We'll go over the equation. We'll go over the equivalent circuit. We'll talk about it because they are used a lot as a generator. We'll talk about characteristics of those kind of things. And if we have time, we'll go over the solid pole. I think we're going to have time. I believe with 5 more sessions, definitely we can go over it. And 6 actually, including today, is only 6 more sessions. Before going there, I told you about the, there is one more thing that I want to talk about induction machine very quickly and finish it. Is the starting of the machine, right? There are three ways to start the machine. If you go look at the torque equation, the first way was, to add the external resistor to the circuit to reduce the starting current. And we saw one example on that one, how to do that one. But the problem with that one is, you have to have a wound rotor machine to have access to the winding of the rotor. And most of the motor, they don't have that. The second method is to use a variable voltage source. So you are connecting AC voltage to the machine, right? If somehow you can control that voltage, I explained it on the soft starter, I said this high restore. If you can start with a small RMS voltage, slowly increase that one. So you are going to be able to control the inrush current in the machine and reduce the starting problem. The third method, this is pretty old. Nowadays with power electronics and everything, God, life is changing really. I think they need to revise these books because lots of these things, I'm going to talk about a few of them, they don't make sense anymore these days. I don't think so anybody will do it, but the third method is still, if you go to the companies like steel companies, those factories, they're pretty old, like 50 years old, 60 years old. They installed all this thing maybe 50 years ago, 40 years ago. The third method, which is a very common method, they call it Y delta starter. Y delta starter. I'm going to just explain it. There's not that equation about the top. So, if you remember, we said, let's say this is the induction machine we have, right? This is the stator of induction machine. I put it as a Y, let's put it. This is Y and this is delta. We can connect it either way, right? Let's see if we have a Y, what's going to happen, and if we have a delta, what's going to happen. We have the same source, three-phase source, to connect to this machine, right? So basically, we are connecting this one to a source. So this is the stator of the machine, right? We are connecting here, or we can connect it this way. So can you tell me what's the difference between these two? The first thing you see here. And the source is the same for both cases. The motor also is the same. We connected the stator winding as Y, or we connect it as a delta. Can you tell me what's the difference between these two? The main first difference you see between these two? Phase and line voltage. How much voltage I'm seeing here? Let's say this is a V. And this is a V also. The same source, right? How much this winding voltage is going to see? V over V. How much this one is going to see? Let's say, I should have put it in the same, but how much this one is going to see? So this voltage is the square root of 3 times that, right? Look at here, if you go back to that, the equation of the torque, we had it, I think, V Thevenin to the power of 2 or something like that for the torque, right? Or the current, because the highest starting torque, high voltage, right? So, and we said one method of reducing the inrush current was to reduce the voltage, right? So if I put it on Y connection, right? How much voltage I'm saying? V over square root of 3. If I put it on the delta, how much I'm saying? V. So basically they start the machine with the delta connection, and they move, they call it a star delta starter. Automatically they change the winding combination, to delta. So basically you start with a reduced voltage, right? When you reduce your voltage, your current is going to be limited. But the advantage of this one, you want to have a high torque, right? You want to have more voltage when you are at the full load, right? So you put the full voltage back here, right? When you get the full voltage, right, full speed, those kind of things, you put more voltage on the machine. So basically you can run higher torque, right? You can run higher load, right? So you start with a start connection, and after that you switch to the delta. There's a kind of breakers, automatically they do this one for you. Basically, if you are going to look at how it does, maybe if you are curious, you have this stator here, right? So you bring all these 6 wires here. Right? So this is basically a switch to, initially it's like this. For example, there is a 1 is connecting all these 3 together. So we have a 1 here, 1 here, here, and there is 3 contacts here, right? They're all going to be connected here. So basically these 3 are shorted together, right? And there are 3 other contacts. Let's put it this way. It's going to be here, it's going to be here, and it's going to be here. So initially when they do this one, they short all these 3 together, right? And these 3 will be connected here. When you get there, what is going to happen? This one is not going to change. This one is going to stay there, right? But this one, instead of connecting here, is going to connect to this side of this one. You know what I'm saying? This one is going to come here. This one is going to come here. And this one is going to go here, right? 3 contacts, they are going to change. So basically from the start, you're going to change it to delta. They're expensive. Still, these are expensive. But they're going to help you a lot to reduce the inrush current. Inrush current for the big motors, you know, like in megawatt size, those kind of things in factories, they cause problem. Because, as I said, for example, the rated current is, for example, 10 kiloamps. So without this one, you're going to get to, for example, 80 kiloamps. Using of this one, it's going to drop it to down to like 20 kiloamps. So from 80, it came down to 20. 20 is much more manageable because you have to put the breakers in the circuit. You have to put the fuse in the circuit, right? If you have a huge current, the fuse is going to burn. Even during the starting, you know, it thinks there's something wrong, you know, because the current is too high. It's going to burn and it's going to stop the motor. This is the one old method they use, you know. But nowadays, you know, as I said, if it's not very important, they use those thyristor one. It's a soft starter. They add that one and they start it very smoothly. If it's a kind of something sensitive and important, they use inverter, 3-phase inverter. You know, that's what we talked about in next course, around 125B. They use inverter. We don't talk about motor control, but the same structure of inverter will be used to start the machine. You can start the voltage very, very, very nicely from 0 to the rated voltage. A perfect sine wave, you know, to put it in the machine. So basically, machine is going to slowly start. You know, but they're expensive. You have to put the control on it. You have to do the circuit with the IGBT, those kind of things. But they are very, very efficient. Very, very, you know, soft in the starting. Very, very, you know, they're going to increase the life of the machine because everything is very perfect over there. You know, there's harmonics and everything is there. But usually they don't use it only for soft start. If it's only for soft start, usually they go with the thyristor circuit. You know, because the thyristor circuit is much, much cheaper and the control is very simple. Just you increase the firing angle from 180 to 0. You change it from 180 to 0 to get to what you want. The next chapter is the synchronous machine. It's chapter 6 of this of the book we have. Chapter 6. I'm going to go up to page because I'm going to go up to page 330 because it starts to talk about power electronics after that. You know, this is the motor drive. I'm not going to go over the motor drive and those kind of things. You know, hopefully one day we'll offer a course for motor control and drive. You know, we go over all this kind of things. But this one, you know, we'll go up to page 330. But initially, the part I'm going to talk about is not in this book. I'm going to use another book to explain the structure of the machine, how it does work, and how we can get to the equivalent circuit of the machine. So we had an induction machine, and I said we called them a synchronous machine. We had a DC machine. Let's just review it quickly. Now we have time, we can spend a little bit more time. Let's go back a little bit back to see what was the DC machine, what was the induction machine, and now we're going to move on to the synchronous machine. If you remember, in the DC machine, we had a stator, right? And we had a DC source here, right? This one was IF. And we had an armature here, right? With the brushes. So basically, this part was DC, right? Output voltage is DC. but we had a commutator. Commutator is like a rectifier, like the one you have in power electronics. You have a full wave rectifier. You saw, if you go back to power electronics, you have a single pulse rectifier, which was one diode, right? You had a double pulse rectifier or full wave rectifier, right? You had a three-phase rectifier, half wave, which was like this. We call it three pulse. You had a 6-pulse rectifier, which is a three-phase, right? So basically, it's going to be like this. It's going to be better. You're going to have a 12-pulse rectifier. You're going to have a 24-pulse. You will have a 48-pulse rectifier. All those ones, right? Basically, the commutator is work exactly. They are different. Just don't think they are the same type of system. Completely different system. But the behavior is exactly like a rectifier. So basically, the AC voltage here will be rectified and will come out of the machine, right? And we see DC output, right? But in reality, rotor is AC, a stator is DC, right? And that was the reason we said we have a core loss only in the rotor, right? Because here frequency is how much? Is 0. There is no core loss here. Going to the induction machine. Induction machines, they are cylindrical. This is a stator. Cylindrical, I mean like this, with the induction machine, with the synchronous machine, we start with the cylindrical, and I say we'll get to hopefully to the salient pole also toward the end. So here we said frequency over here was SFS, right? And we said S is a very small number, SFS is going to be a very small number. Basically, the induced voltage and current here is going to be a DC current almost, right? Zero frequency, right? There is no core loss here, and here is this. Now we're going to go back to, we're going to go to the induction, synchronous machine. Can you look at this, look at this one and tell me what could be that one? What could we have for the synchronous machine? We had the AC, DC, we had a DC, AC. The synchronous machine is something between this and this. It's going to be something like this. Just I'm going to put the salient pole here because it's easier to draw it. It's a DC like here, but it's in the rotor. And the stator is AC. The stator is AC. So we're going to start the synchronous machine. And one more thing I forgot to say. Here, the rotor was rotating with what speed? Right? And can you tell me what speed this rotor is rotating? This one rotates with an S. This one rotates with this one. They call this one also asynchronous machine because its rotor is not rotating with the synchronous speed. And you can see when you say synchronous machine, so the rotor is going to rotate with what speed? Synchronous speed, right? So DC machines also are kind of, you can put it in the category of the synchronous machine, but because of complete different structure, we call them DC machine. Synchronous machine, they have a different type. They have a wound rotor, like the induction machine. Majority of them, they are like that. Look at here, when we have this one, if we have a field here, we are going to have a magnetic field like this, right? And basically here is going to be N, here is going to be S, right? Basically we are creating a fake magnet, right? So they call this one wound rotor because we have winding here on the rotor, right? They have another type is called permanent magnet rotor. Basically this one is going to be by itself a permanent magnet, right? So it doesn't have to have any winding. So it's a permanent magnet. They have another type they call it switch reluctance machine. Switch reluctance machine you had in the homework. The one was like this. I think you had one homework like this. Or maybe you had just needed 2 poles.